Sharing screen. And okay, so G-eng 200, and today is March 22nd, 2021. And topic for today is parameter estimation. And I want to do a few announcements before we start. The first one and most important one is that the optional, let me write optional, MCQ, which is a multiple choice questions exam, will be tonight. Tonight at 8 p.m. There will be 26 questions. You are required to answer 25. One is bonus. So if you have one wrong and the rest are good, so you still have 25. It will be marked out of 25. You'll have 50 minutes to finish the exam. So 2 minutes per question. There will be no calculations that will waste time. It's mostly concepts. So make sure that if you want to prepare, just prepare. Read the solution of the midterm that I uploaded well. So I covered most of the concepts in the midterm in an MCQ question. So make sure you fully understand the solution that I uploaded. Also, there will be no backtracking. So you will not have access to all questions at once. You will have question by question. So sorry. So make sure that you watch your time. And yeah, just watch your time and have Gaussian tables and probably the book or your formula sheet ready. With you, so that you can refer to them for answering the questions. No discussions allowed between students, and no help from any other sources. I will, of course, now we will not be able to monitor this, but I will count on your ethics for this. So it's up to you to abide for those ethics. Also, the exam will have a password that will be mailed to you a few minutes before the exam. So that's it. So it's, I hope you will all do well in this exam so that you can raise your mark for the first midterm. And again, this is optional, but I urge all of you who scored, regardless of your score, because this should not harm you. If you do bad in this and taking the average will affect your midterm mark, then I will keep your midterm mark. So this exam should not harm you. It might help you, but it should not harm you.
Doctor,
Yes.
those who didn't take the makeup, can we do this one too? And you take the average?
Yes.
Can we
Yes,
take
for
it
sure.
tonight?
Yes. So this is for everyone. Yes, it's for everyone. I will not have another one. This is optional, so for everyone, even for those who did not take the midterm.
And you will take the average?
Yes. If it will help you, I will take the average if the average helps you. So if one of those who did not take the midterm, if you take the exam tonight and for some reason you did not do well, and you do well on Wednesday, then I will not take the MCQ exam into consideration. So all of you, I urge all of you, there will be no other chance for this exam. So I urge all of you to take it. Right. Second announcement, for those who missed the midterm, makeup will be on Wednesday, 24th of March, during the class time. So on Wednesday, for those who missed the midterm, you just come to my office, F112, come to and bring your medical excuse. Or quarantine certificate. And this will be your last chance to take the exam. If somebody misses Wednesday, there will be no time to take the midterm anymore, and you need to do whatever you want with the course, if you want to continue or not. But I will not be able to do another chance for the midterm. So these are the announcements. I hope all will do well tonight in the MCQ, and for those who missed the midterm, I wish you the best on Wednesday. So for that, on Wednesday, I will be recording the lecture, because I will be with the students who are taking the makeup during the class timing. So I will record the lecture for Wednesday, and I will upload it to Blackboard. Okay. Back to our course, and as you might recall, before the break, we started with the statistics part of the course. So recall. And we said statistics generally is two parts. The first is descriptive statistics, like presenting data in a meaningful way. And the second one is inferential statistics, where data is used for taking decisions. And inferential statistics is usually divided into estimation and hypothesis testing, and estimation is usually divided into point estimation and interval estimation. Some books, they present estimation as one estimation, which is parameter estimation, and then they call interval estimation as confidence intervals on the parameter estimation. So that should be fine. So we'll be covering this week. We'll talk about point estimation. Next week we'll talk about interval estimation. The week after we'll talk about hypothesis testing, and that will conclude the course of probability and statistics. Right. So with that in mind, with this big picture in mind, let's start talking about point or parameter estimation. And basically, from now on, what we will do, we will be studying the population, what's a population? Anyone recalls what's the definition of a population? If you recall, a population, we said, is any collection of objects that have something in common. So students of Qatar University, they form a population. People in Qatar, they form a population. Products of a certain factory, they form a population. So any set of objects, any collection of objects which have something in common, they are a population. So in the different techniques that we will be talking about, we will be focusing on a certain population. Sometimes we know the distribution of the population, and sometimes we don't. Sometimes we know the distribution of weight of people in Qatar, for example. We know it's normal distribution. The waiting time, if you want to study the waiting time in a bank, we know that it's exponential distribution. So sometimes we know the distribution, sometimes we don't. Right. Then, so we'll focus on a certain population, and then we will not get into collecting a sample, but we will assume that a sample is collected consisting of x1, x2, all the way to xn. So we assume that we will collect a sample. So if we want to study the weights of people in Qatar, we assume that we'll collect a sample of certain size n, and you, and like pick randomly, whatever, 20 people or 30 people, and measure their weights. And then the weight of the first one is x1, the weight of the second one is x2, the weight of the nth one is xn. طيب, and then what will happen? Then this sample will be used to estimate an unknown parameter of the population. So we don't know the average weight people in Qatar. Mu. What's mu? The mean of the weight of people in Qatar. We don't know it. So this is a parameter we want to estimate. So we'll learn about how to estimate this mean. We don't know the ratio of people with diabetes in Qatar, for example. What's the ratio? Is it 20%, 30%, 40%? What will be the way to estimate this ratio? We collect a sample and then we'll process this sample to get the parameter that we are interested in. That's why we are talking about parameter estimations or point, since each parameter has a single value. So we'll be estimating a single value, which is the value of the parameter. So in most cases, we'll either deal with the mean of the population, the variance of the population, the what we call population portion, like the ratio of people who have something, the ratio of products that are defective of a certain factory, and so on. So these are the kind of parameters that usually we are interested in estimating. Let's have some important notes. First note is the samples are random variables. Which means that x1, x2, all the way to xn are random variables. Why is that? Why are the samples random variable? Very simply, before you go and collect the sample, do you know the value of the sample? We don't know it, صح? Before you go and pick people randomly and ask for their weights, you don't know their weights. And if you repeat this experiment every day, you go and collect different set of sample, you'll get different weights, right? So the sample, the values of the samples are random variables. So x1, x2 up to xn are random variables. So this is the first important note that you should keep in mind. Second important note is that the distribution says they are random variables, then they have a distribution, right? So the distribution of x1, x2 up to xn follow the same distribution of the population. So what does this mean? So if we are dealing with a normal population or a Gaussian population, then x1 will also have a Gaussian distribution. x2 will also have a Gaussian distribution. xn will also have a Gaussian distribution with the same mean of the population and the same variance of the population. Okay? Third note, as the samples are random variables, then any function of the samples which we call a statistic is also a random variable. And in general, a statistic is denoted as capital theta hat, and it's a function h of x1, x2, all the way to xn, which is function of the samples. So if the samples are random variables, then if you take those samples and you add them, or you multiply them, or you divide them by any number, so you do any function of them, the resulting process, if you process them, this processing, we call it a statistic. So a statistics is just collecting samples and then process them in a certain way, adding them, dividing them, as we will see. We'll design those estimators. And once you do that, it's like you are carrying a function of those samples. So we call it a statistic, and we give it the notation of big theta hat. And we use such a statistic, theta hat, to estimate unknown parameters of the population. Which we denote as small theta. So for example, the mean mu of a population is an example of theta, the unknown parameter. Let me give one more note, and then we'll give an example to clarify what's this big theta hat, small theta, and the last one, which is what we call a point estimate of the unknown parameter is denoted as small theta hat, and which is the numerical value resulting from big theta using a specific sample. So what does all of this mean? Let's give an example to clarify what I have been talking about. Assume we are interested in estimating the mean weight of children between ages 5 and 12 and we know that the distribution is normal. So somebody is interested in finding the mean weight of children between ages 5 and 12, and we don't know mu. We know it's a normal distribution, but we don't know its mean. So we want to estimate mu. So first step is collect a sample. Let's say of size n equals 4. It's very small sample. So you went out, each one of you went out. So first one, so you collected this sample, x1 of equals 25, x2 30, x3 29, and x4 equals 31. So how did you collect this sample? You went out asking for, looking for children and ask, is your age between 5 and 12? If yes, what's your weight? You collect. You need four samples. So what's the unknown parameter? So small theta, what's small theta in this case? Theta is mu in this case, the mean. What's unknown? Mu. What do you think the best way to estimate mu based on the sample? What is the estimator? Big theta hat. What do you think the best way to use this sample that we collected to estimate the unknown mean of the population?
I think since it's a normal distribution, we assume that the age will be in the middle. Most of the children.
So how can you use this data that you collect, 25, 30, 29, and 31? How can you process it? How can you use this data to get an estimate of mu? You tell me I'm looking for an estimate for mu. I need a number. What's your best guess? How do I take, for example, x1, and you tell me 25 is a good estimate for mu, or the maximum is 31, or what should we do with those numbers? What do you think the best way?
Can I answer here?
Yes.
We find their mean. Maybe.
So the most intuitive way is to calculate x bar, right?
Yes.
Yes. So x bar, which is, we know that, will be x1 plus x2 plus x3 plus x4 over 4, will be a good estimate for the mean. So x bar in this case is 25 plus 30 plus 29 plus 31 over 4, which is 28.75. So x bar is a function of the samples, right? Function of the samples, and this is my statistic that I talked about, or estimator. This is my estimator. This is how I estimate the unknown mu. Mu is the unknown parameter. Mu is the unknown parameter, which is theta. X bar is my big theta hat. And what's 28.75? 28.75 is my point estimate. The estimate that 1 second, let me close my door. Sorry for this, I had to close my door. People are laughing in the corridor. So the point estimate is the numerical value from applying the estimator to the sample. So we have three things. We have small theta, which is the unknown parameter, in this case mu. We have big theta hat, which is the estimator, which is the function that I will use in my estimation. In this case, it's x bar. And we have small theta hat, which is the estimate itself. And small theta hat is the numerical value that results from applying my estimator on the samples that we have collected. So based on this discussion, let me ask you this. So if I tell you we are interested in studying in estimating the mean of the weight of children between the ages of 5 and 12. And we will use the estimator will be x bar. And I want each one of you to go and collect a sample of size 4 and come back to me with a point estimate for the mean. All of you will get back to me with the same point estimate, with the same theta, small theta hat? Yes or no?
No.
No.
So each one of you will collect a different sample, x1, x2, x3, and x4. It will be different for each one of you, right? And then when you apply x bar, when you calculate x bar, it will give you a different estimate, even though all of you are using the same estimator. What's the estimator you are using? X bar.
X bar.
Right? So all of you will use the same estimator, but since each one will have a different sample, each one will give me a different point estimate. However, I would expect that those estimates will be close to each other, right? I would expect like one of you will give me 28.75, maybe the second one give me 29.5, third one will be 30, the fourth one will be 27.5, and so on. So you'll come up with different estimates, even though you are estimating the same parameter, which is mu, and you are using the same estimator, which is x bar. Okay? So let me write this down. So since samples are random, different people using the same estimator, x bar in this case, will get a different point estimate, which we call theta hat, small theta hat, for the unknown parameter u, which we denote as small theta. And of course, theta bar is our big theta, which is big theta hat. So we have an estimator, which is the mathematical formula that you apply for your samples. We have unknown parameter, which is the thing that is unknown to you, and we are trying to estimate, which is small theta. And we have the estimate itself, the numerical value that you get when you apply your estimator to a specific set of samples. Let's do some examples.
Sir, I have a question.
Sure.
If someone may get extreme value like 45 or 50, how do we deal with this?
Usually we don't, in this course we will not get into the etiquettes of sampling, but as we will see, the way to overcome having extreme mix sample size n, and we'll talk on I think on Wednesday, we'll not be able to, about the error in your estimator, and we will see that the error is inversely related to n. So the larger the sample size, the smaller is the error that you are getting. So the only way is to do the correct sampling and to use large sample size. Those are the two ways of preventing you from getting an extreme estimate for your unknown. Okay?
Okay, thank you.
Sure. So some popular popular estimators, let's say estimators, not estimates. Estimators. So if we are talking about mu, we use, what's the best way of, or not the best way, and what's the popular way or an intuitive way? If we don't know the mean, we conduct a sample and then we use X bar, right? To estimate. So mu hat equals X bar. This is my estimator. If we don't know the variance, how can we estimate it? Any idea? How can we estimate the variance? We talked about a way of, from the data, to have an approximation for the variance. Anyone? We talked about the sample variance, right? We use S squared, the sample variance. So my sigma square hat is S squared. Remember S squared? How is it given? Which is summation from I equals 1 to n xi minus x bar squared over n minus 1. This is a way to estimate the variance. Also, for if we are interested in finding the ratio of people who have diabetes in Qatar. So if you go out and collect a sample of 100 people, so that you ask each one if he or she has diabetes or not, what will be the best way to use this data to have an estimate for the ratio of people with diabetes in Qatar? How do you process this data? Anyone?
We choose random samples.
Okay. And then what do you do with the random sample?
And then we generalize the data we got.
No, but how will you process your data? So you recruit someone to go out, and he will give you back 70 or 100 forms, and each one there is a tick. Yes, I have diabetes. No, I don't have diabetes. How will you use this data?
Doctor, does the we know that older people have diabetes. If we went to a place where there is only old people, we have a different probability than if we went to, let's say, a mall where there's like
That's
mixed.
again. Let's not mix things together. We're talking about how to do sampling. We said the way to avoid extreme or bad estimates is to do wrong sampling. Wrong sampling means, like you said, either you go to a place where having older people, or a place where rich people, or so it's this is the art of sampling. I'm not talking about that. Assume that we did a correct sample. We went out and we collect a very nice sample that represent different ages, different economic classes, different nationalities, different. So you have this sheet in which each sheet has, yes, I have diabetes, no, I don't have. You have 100 of those. How do you process the data to get the ratio of those who have diabetes? Very simple way.
From the given papers, like we, if for example, if we have like 100 paper, and 45 of them said that they have diabetes. So we're gonna assume that 45% of people in Qatar have diabetes.
So you divide, right? You divide those who said yes.
Yes.
Divided by the total number, which is 100.
Assuming that the samples they were chosen randomly.
I'm not talking about the sample we assume for a random sample and good sample. How do we process? We're talking about how to process the data. So yes, so we divide those who said yes over the total number. This will give me an estimate of the ratio. So we call this population proportion, ratio of the population who have specific quality. And this is called P. How do we estimate it? We use the estimator P hat equals X over N, where X is the number in the sample who have the mark or the ratio, the quality you are looking for. For example, have diabetes. So if 45, as you said, they have diabetes, then your estimator is 45 over 100, so 0.45. You would come back to me and you tell me, okay, I estimate that 0.45 is the ratio of people in Qatar who have diabetes, or 45%. Somebody else will do the same, use the same estimator, will collect different sample, maybe he will get 41, he will come back to me and said, my estimate is 41%. Fourth one, 39%, 42%, and so on. However, if we are doing correct sampling, we'll expect that all of those estimates will be close to each other. Okay? Okay, I think it's a good time to take the absence. 1 second. In the morning class, I have my TA with me. Please log into your Blackboard so that you can mark in your attendance.
Doctor?
Yes.
The example we just discussed, is this the same thing as generalizing the data?
Is it what?
The same thing as generalizing the data?
Of course, this is what statistics is all about. Statistics is about collecting samples, coming up with decisions, and generalizing the decision to the whole population. So this is all what they do. Remember, in the elections in the United States, just before the elections, they just call people and ask them whom you are going to vote for, and they said Biden or Trump, and like if 25% of those who said we'll vote for that person, then they said, okay, we expect 25% of the people will vote for Trump or vote for Biden. They did not ask everyone. They asked a representative sample about this, and then they generalized the decision to the whole population. Okay, so L02, and then attendance, and then sorry, it's a bit slow. I hope you are all ready. Okay, start checking in. We'll pause for 1 minute for you to check in your attendance. It's open for 3 minutes, but try to do it as soon as you can.
Okay, but Doctor, I have a question regarding to the same example we just discussed. You
okay,
said,
can you just can you wait for 1 minute? Let's pause for 1 minute and then
yeah, sure,
can ask your question.
inshallah.
Sure. Oh, seems that okay, mine. Okay, let me think. I need to start sharing again. Okay, what's your question?
Yes, Doctor. Doctor, you said in the previous example that if there is a specific procedures, if we do them, we will get the same approximations.
Well, not the same. We'll never
Or
get
similar.
the exact same, but they should be close to each other. Yes.
What are these procedures? If
We
they're
said
not
two
like
things. We have representative sample, good sample, and large sample. So the sample should be representative and large in size. If you do those two things, then you will get good estimation of the unknown parameter that you are looking for.
representative, I didn't get this part.
Representative means it represents all categories of the population. So if you are talking about the weights of children between ages 5 and 12, don't collect your sample from only those who are 5 or 6 years old. You have to scan all, like from 5 to 12. Like you divide your sample like into like I will have 10 children of age 5, 10 children of age 6, 10 children of age 7, and so on. And then don't take all of your sample from a poor area. If we have a big country with poor area means children are underweight, or a wealthy area, or you get me? So depends on the scenario. Depends on the scenario you are doing. You have to collect your sample accordingly. Like in Qatar University, we have CESRI, which is the Social Science Research Institute. They always do this kind of studies. And at one point, they wanted to ask they wanted to do a survey on the opinion of housemaids. So they collected sample of housemaids and people who have housemates. Of course, you will not go to industrial area, for example, and ask people there if they have housemates. They don't have housemates, or they give you, even if they answer you, it will be a wrong answer. So you have to select the areas where families, like mainly Qatari families or wealthy Arab families or wealthy foreign families, who usually have maids. So you have to collect your sample from the right place. Okay.
Okay, clear. Thank you, Doctor.
Sure. Right. So let's talk about the sampling distribution and the central limit theorem. So now we said our estimators are random, right? They are function of the samples which are random, then our estimators are random. So our estimators are random variables, which means they have distributions or probability distributions, which we call sampling distributions. So, for example, X bar has a certain distribution. Which we will find. Because it's a random variable. So, what's the theory for that? We'll have two versions. First one is, given that a sample x1, x2, up to xn of size n is taken from a normal distribution or a normal population. This is a strong assumption with mean, mu, and variance sigma square. Then X bar is also, or X bar has a normal distribution with, so if x1, if we have a normal population, to start with, we have a normal population. I tell you in advance that the distribution of the weight of children between ages 5 and 12 follows a normal distribution with a certain mean mu and certain variance sigma square. We don't know the mean and the variance, but we know that it's normal and has certain mean and certain variance. So based on this, and based on the important notes that we mentioned earlier on, we said that the distribution, this is very important note, we said the distribution of the sample x1, x2 follow the same distribution of the population. So x1, x2, xn also are normal in this case. So if the samples are taken from a normal population with mean mu and variance sigma squared, then x1 and x2 and xn are normal distributed. How about x bar? I'm saying here that x bar is normal distribution. Why? What's x bar again? X bar is what? X bar is just the summation of x1 and x2 and xn divided by a constant n. So what happens if you add a normal random variable to another normal random variable? What do you get? Remember the reproductive property of normal distribution?
You also
We
get
said
a
if
normal random value.
we get a
find
normal
this-
random variable. If you add normal random variables, you get another normal random variable. If you subtract normal random variables, you get another normal random variable. So x bar has a normal distribution. And what we need to do is to find its mean and its variance, because the normal distribution has a mean and a variance. So let's see what's the mean of x bar. What's the expected value of x bar? Expected value of x bar is just the expected value of x1 plus x2 plus xn over n. And n is a constant, you can take it outside. So expected value of x1 plus x2 plus xn. So this one over n. And then samples are independent. What's expected value of x1? What's the mean of x1?
The first value.
Yeah, so the sample, first value of the sample, what's its mean?
It's the same for all, right?
It's the same, which is the same for the population, right? We said the samples follow the same distribution of the population. And we say here that population has a mean mu and the variance of sigma squared. So again, recall the important note. Recall the note up. x1, x2, xn have the same distribution of the population. So they all normal of mu sigma squared. So all of them, x1 has a normal distribution of mu and sigma squared. x2 has a normal distribution of mu and sigma squared. So what's the expected value of x1? It's mu. What's the expected value of x2? It's also mu. What's the expected value of xn? Is also mu, which means that 1 over n times n mu, which is mu. So also x bar has the same average of the population, which is mu. طيب. So now we know that x bar is normal. We found its mean. What's its variance? What's the variance of x bar? The variance of x bar is just the variance of 1 over n of x1 plus x2 plus xn. 1 over n is a constant. If I take it outside the variance, what happens to it?
Stays the same.
So we said variance. Remember, variance of AX equals what? Remember? Anyone? Let me write it here. If you recall, variance of AX equals A squared variance of X, right? If you have a constant, it goes out to be squared. You have to remember this for tonight's MCQ question, MCQ exam. So this is one of the properties of the variance. So if you multiply a random variable with A, it's like you are multiplying its variance by A squared. So here, then this will come out as 1 over n squared, and then this will be variance of x1 plus variance of x2 plus variance of xn. What's the variance of x1?
It's the same, sigma square.
Sigma square, right? For all of them. It's the same as the variance of the population. So in this case, what do we have? So what's this? What does this mean? It means that X bar has a normal distribution with mean mu and variance sigma squared over n. So X bar has normal distribution of mu and sigma squared over n. Which is nice. And we'll see what does this exactly mean next lecture. But basically, what happens if n goes to infinity?
0. Variance 0.
Variance of X bar will become 0, which means
Yes.
what? If the variance is 0, remember what's the meaning of the variance?
Means the dots or the points, they are like so spread. No, sorry, they are almost similar.
Okay, which means what? Which
0,
means
we
that
have just one value.
we have only
One
one
value
value. So
fixed.
which means what? If I ask you to estimate the mean of the children in Qatar between ages 5 and 12, when n goes to infinity, it means that each one of you went and asked all children about their weight, and you calculate the X bar. So you all will give me the same value, right?
Yes.
If you all went and asked all children, then you will all come back to me with the same value, which is exactly mu. In that case, you all got the exact unknown value of mu. This is what mu. We'll talk about this more, but this is for now what this means. Right. This was the first case, which is we have a normal population. What if the population is what if the population is not normal, or its distribution is unknown? In this case, we do the central limit theorem. And basically what it says if x1, x2, xn are random samples size n from a population, any population, not necessarily normal, with mean, mu, and variance, sigma squared. So we know that we have a population, it has a certain mean mu and a certain variance sigma squared, but it's not necessarily normal. Then mean x bar not then, sorry. Sample x bar. Then the distribution of x bar minus mu over sigma over square root of n as n goes to infinity is a standard normal distribution. Which means what? Which means now, if I tell you that the population we are dealing with is a normal population, then regardless of your sample size n, x bar has a normal distribution. However, if the population is not normal, then x bar is also has a normal distribution, but only when n is very large. As n goes to infinity, then x bar will have a normal distribution. And this is something that you can check this yourself by, if we have a uniform population, like discrete in this case. So if you throw one dice, what will be the distribution? You will have, you are averaging only sample of one, so you will get, there is nothing to average, right? You will get in principle all 1, 5, all outcomes will have the same probability. However, if you throw two dice and calculate x bar, what do you get? What are the possible values if you are averaging two dice? So you can still, the smallest you can get is 1, the largest is 6. But in this case, you also can get 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, and 6. And you will see that the number that you'll get the highest time is 3.5. Why? Because 3.5 can be out of 4 and 3, or 5 and 2, or 6 and 1. So you have more chances that you will get rarely you will get 1 and 6. So you start getting something like this. Try if you have 5 dice, you will start getting something like this. So you'll have you will start getting the shape of a normal with more chances, because you are averaging 5 dice. So you'll get something something like this, and next your computer assignment you will do this, so that you can see that the shape of the distribution will become closer and closer to the normal distribution. So the bottom line, to conclude with, the bottom line is X bar is exactly normal for normal population, is approximately normal for any population as n goes to infinity, if n is large. Okay, so I'll stop at this point, and we'll pick it up on Wednesday. As I said, Wednesday will be a pre-recorded lecture, and for those who missed the midterm, you can come on Wednesday. And I advise all of you to take the exam tonight. It will not harm you. It either will help you or it will not. And I wish you all the best. Check your email before the exam so that you receive the password for the exam. If you have questions, I will be happy to answer them now. And if you don't, you can just